This video is about differential equations, and this topic is split into three components. The first component is just introducing you to differential equations, describing what it means to solve a differential equation. How would you confirm that a claimed solution truly is the solution? And then the second part is about a particular class of differential equations called separable differential equations. And the last part is about a second type of differential equations called linear differential equations. And we're going to largely spend our time on what are called first order differential equations, which have the following form. A first order differential equation relates the first derivative of some mystery function to the mystery function itself. So an example of that is the statement dy by dx is equal to y. So if we think about what that's saying, it's saying there's an unknown function y. And its property of whatever this function is that if we take its derivative, it doesn't change. The derivative of the function is the function itself. And you might have, at first glance, you stare at that, you think about it, you might have the answer. You might know what function that is. Another differential equation I've written there in red is the derivative of the mystery function is equal to x squared times the mystery function squared. And this is not the type of thing you're just going to think about. Think really, really hard and come up with the answer. We need a mechanism or an approach or a recipe that we could use to determine what solution fits this criteria. Later on, I'll describe why are we doing this? Like, why are we creating and solving differential equations? So let's go back to that example, dy by dx is equal to y. The derivative of some mystery function is equal to the function itself. One function that behaves that way is e to the x. The derivative of e to the x is e to the x. So that's the solution, right? Well, not so fast. What about 5 times e to the x? The derivative of 5e to the x is 5e to the x. How about negative 7e to the x? The derivative of negative 7e to the x is negative 7e to the x. So there's a whole bunch of solutions. So there's an infinite number of them. Put any constant in front, and there you have it, another solution. We can group them all together into one family of solutions by saying that the solution y is equal to some constant, which we'll call c, multiplied by e to the x. This is very different from integration, or at least direct integration, where we get this plus c, this constant integration. With differential equations, we will always get an arbitrary constant, but that arbitrary constant is sometimes added, sometimes multiplied, sometimes it's in an exponent, sometimes it's somewhere else in a function. It can appear in different spots depending on the details of the differential equation. What does it mean to confirm a solution? So suppose we have a puzzle, like the one that's given here, that y prime is equal to 3 divided by e to the y, with a condition. So in addition to this mystery function having to fit this criteria, there's another criteria it has to fit, that the mystery function evaluated at -1 has to equal to 0. Suppose that claim, or that question is met with a claim, that the function that fits that criteria is given by y equals a ln of 3x plus 4. We could test that claim by checking both of those conditions against that function. So let's look at the easy one first, the easy condition. Y evaluated at -1 is equal to 0. We can take our function, replace x with -1, and make sure we get an output of 0. So y of -1, that's the ln of 3 times -1 plus 4. So the ln of -3 plus 4, the ln of 1, and the ln of 1 is 0. So that part does meet the condition, but we can't be confident about this thing solving the entire puzzle unless we also confirm that the derivative of the mystery function is equal to 3 divided by e to the power of the mystery function. What we'll do is we'll substitute our mystery function into the left side and to the right side, and we'll work away at the expression until we can check, or until we're sure that left side is truly equal to right side. So on the left hand side, y prime, that's telling us to take the derivative of y, so I put the derivative of the ln of 3x plus 4. On the right hand side, we have 3 divided by e to the y, so I just replaced y with the ln of 3x plus 4. Now, how do you take the derivative of the ln of 3x plus 4? Well, it's the derivative of ln of w prime over w. So that's 3 plus 0 over 3x plus 4. On the right-hand side, we have in the denominator e to the ln of something, and the cancellation law allows us to cancel the e to the ln, and we just get the argument of that log function, 3x plus 4, and now look what's there. On the left, 3 over 3x plus 4. On the right, 3 over 3x plus 4. They match. So this proposal for a solution we can confirm is correct. Just to show you what a second order differential equation looks like, here's one, y double prime plus y prime minus 6y is equal to 0. So this is a very horrifying type of differential equation to solve just by trial and error, just by guessing, unless you know how you're supposed to guess for something like this. It also has a condition that this mystery function evaluated at 0 is equal to 8. And all we're asked to do here is to show that y equals 3e to the 2x plus 5e to the negative 3x actually solves this puzzle. So what we're going to do is get all the ingredients. So first I'm going to find y prime. Y prime is the derivative of y. So we'll have the derivative of 3e to the 2x, which is 3e to the 2x times 2 from the chain rule, plus 5 times the derivative of e to the negative 3x. Derivative of e to the negative 3x is e to the negative 3x times negative 3. And we can simplify that just by multiplying the constants together. So 6e to the 2x minus 15 e to the negative 3x. The next thing we need is to find y double prime. I'm finding these pieces because I'm going to take them, once we have them, and plug them into y double prime plus y prime minus 6y is equal to 0 and make sure that this function does what it's supposed to do. Okay, y double prime, I'm going to take the derivative of y prime. So the derivative of 6e to the 2x, that'll be 6e to the 2x times 2 for the chain rule. And then we have minus 15 times the derivative of e to the negative 3x, so e to the negative 3x times negative 3. And then we can simplify, multiply the constants together. 6 times 2, 12 e to the 2x minus plus 15, negative 15 times negative 3, positive 45 e to the negative 3x. Now, combine into y double prime plus y prime minus 6y and check it equals 0. Because that's what our differential equation says has to happen. So let's take those pieces. So we got y prime is 6e to the 2x minus 15 e to the negative 3x plus, oh, I should put them in order. It's y double prime first. So 12 e to the 2x plus 45 e to the negative 3x. So that's the y double prime part. And then plus y single prime, 6e to the 2x minus 15 e to the negative 3x. And then minus 6 times y, so minus 6 times 3e to the 2x plus 5 e to the negative 3x. I'm going to check, is this equal to 0? I'm going to multiply that negative 6 at the end through the brackets. And then after we do that, we'll just collect like terms. So minus 18 e to the 2x and minus 30 e to the negative 3x. Is this equal to 0? Let's collect like terms. So looking at all the multiples of e to the power of 2x, I'll just underline them all. We got one there, and one there. So we have 12 plus 6 minus 18 times e to the 2x. And now we have e to the 3x terms. plus 45 minus 15 minus 30 e to the negative 3x is equal to 0. And we get 0 times e to the 2x plus 0 times e to the negative 3x is equal to 0. We get 0 is equal to 0, which is true. And we have one more step to do. Now check that y of 0 is equal to 8. So y at 0 is going to be 3 e to the 2 times 0, so 3 e to the 0, plus 5 e to the negative 3 times 0, so 5 e to the 0. That'll be 3 times 1 plus 5 times 1, and that's 8. So that's also correct. That's what is required here. So in these types of differential equations puzzles, in these questions, we see that the typical format is to have a statement about the derivative of the function as it relates to the function itself, and to have information about the function's value at some x coordinate. So what is the output of the function at some x value? This combination of pieces, this combination of requirements, is called an initial value problem. And we're also going to call things initial value problems even if the value of the function isn't known at, let's say, 0 or 1. Even if the value of the function is known at 20, the structure of the problem is the same. It has more to do with computational aspects, why it has that name. So here's an example initial value problem, that the derivative of the mystery function is equal to negative 3 multiplied by the mystery function, and the mystery function evaluated at 0 is going to give you 6. We're going to learn how to solve this from scratch without seeing what the answer is, without just here's a form of the answer, find C, like what I'm about to do. But let's say we go through that process and we find that the solution to the first part, the top requirement, that the derivative of the mystery function is equal to negative 3 times y, we find that the solution to that part is c times e to the negative 3x for some arbitrary constant c. We would then find c by using that initial value. So replace x with 0, replace y with 6, and rearrange and solve for c. And that tells us in this case that c is equal to 6. And that our general solution that solves both requirements is this one. Y is equal to 6 times e to the negative 3x. I invite you to go and check that it meets both of those requirements. Now, it looks like we're playing math games. It looks like we have these statements about derivatives. We've already been talking about derivatives, we've been talking about integrals, and this is just a new type of puzzle to solve. And there's a lot of truth actually to that idea or that sentiment, if that's how you're feeling right now, that we're just throwing puzzles at you. And kind of, yeah, we are. It's about problem solving. It's about taking techniques and figuring out what you're supposed to do for what types of problems. It's an extremely transferable skill, independent of the mathematical component of it. That's one type of response to this is just a math game. It's just a math puzzle. Just find x, but in a different form. The second answer to what are we doing and why are we doing it is that you can do useful things with differential equations. You can model reality. I'm going to give you two silly sounding examples and then show you that they're actually not that silly. If we want to model the mathematical behavior of, say, a population of bunnies on an island, where the quantity of interest was the population itself, like how many bunnies are there. I'm going to make a distinction between islands that are very large and islands that are small. And a large island is an island that has maybe essentially unlimited food. There's no worry about running out of food, running out of space, running out of little hidey holes for the bunnies to live in. It's an open huge island. The sky is the limit in terms of how many bunnies the island can hold. And the type of model we may come up with is we would say the rate of change of the population, dp by dt, the rate of change of the population with respect to time. Let's think about cities for a moment. Like, let's say a city with a population of 100,000 people. Maybe you'd expect 1,000 babies to be born every year in a city of that size. If you were to multiply the city size by 10, it's a reasonable proposal that the number of babies born would also multiply by 10. If you have 10 times as many people, you're going to have 10 times as many babies. Right? It's reasonable. It's not going to be perfect, but this is about making a reasonable mathematical model. So I would say then that the rate of change of the population is going to be proportional to the population itself. I'll say it's equal to k times the population p for some growth rate k. So if k is very large, then you're going to get a higher growth rate. If k is very small, you're going to get a lower growth rate. And a reasonable question to ask would be, what about deaths? Well, if you take a population of 100,000 and you'd expect 800 deaths per year, what would you expect if you multiplied that city's population by 10? Well, you'd expect 10 times as many deaths. You'd expect, instead of 800 deaths, you'd expect 8,000 deaths. That's not perfect, but it's a reasonable assumption. It's a reasonable approximation. And that fits into this as well. We would have components that would contribute to increases and components that would contribute to decreases, and they would both scale according to what that population is. What this gives you, we would find that the population is equal to A times e to the kt for initial population A. And if I draw a quick sketch of that, that's just an exponential function, positive exponential function, so exponential growth. And you would have seen this in an earlier mathematics course when we talked about exponential growth and exponential decay, or whatever terms you used. So that's p is equal to a e to the kt. And it keeps growing forever. It goes up, 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 never goes back down, never decreases. How about bunnies on a small island? So what's the difference here? Well, on a small island, you start running out of space. You start running out of food. You start running out of little places for them to hide. And the population cannot grow like that. And the graph of the population, what it would appear is like this. And you can see this in all types of experiments with biological sciences, with bacteria in petri dishes. You can see this in natural populations when you have predator and prey systems. So not predator and prey systems, everything except that. So you have an initial population. It grows exponentially until it starts feeling the stress of its environment, where it's feeling, well, we're running out of food. And the population growth slows down and it starts leveling off. And it starts approaching the level at which the environment can support. So let's say the environment can only support 1 million bunnies on this small island. The population curve is going to slowly approach 1 million. This isn't perfect. This isn't real. This isn't necessarily realistic either. Populations can do this and then crash. Those types of things can happen. And it's about the dynamics. It's about what are the different influences, what are the different factors. So predators, if there's more bunnies and there's anything on the island that can eat bunnies, and more bunnies means more food for those things. And you get these complicated dynamic systems, coupled differential equations, which we're not going to talk about. So for our purposes, if we're only worried about the interplay between the resources available for the animal and the population of the animal itself, the curve would look like this. It's going to be exponential growth at the beginning, and then it slows down and slowly approaches that carrying capacity of its environment. Now, how do we construct a differential equation that gives us that behavior? So I want the rate of change of the population is equal to something that has some exponential growth in it, so k times p. Then I want the rate of change of the population to punish growth that gets very close to the carrying capacity. So I'm going to let m equal the carrying capacity of the island. How many bunnies are there? Or how many bunnies can you support? If I do m minus p, kp times m minus p, then what's going to happen is when p approaches m, now I should label what m means, with carrying capacity m. When p approaches m, dp by dt is going to approach 0, because we'll have, let's say, m minus m, we'll have a 0 there. dp by dt is equal to 0. And look what happens if the population exceeds the carrying capacity. Say our carrying capacity is 1,000 and we have 2,000. Well, then our dp by dt is going to be negative. We'll have a negative rate of change. So that's going to drive the population down, decrease the population. And if we go through the process that we'll learn later about how to solve this differential equation, we will get the curve that's on the right. So very simple reasoning to construct the differential equation, and it gives us a reasonable type of result, a reasonable type of dynamics. Now this is about bunnies, but what about us? We're animals. We have a population. We have an environment with a carrying, presumably with some type of carrying capacity. And there were concerns for quite a long time that the human population was going to do something dramatic and scary. Some concerns that the human population was going to explode. So here's a piece of a graph of the human population curve. The blue is the population of humanity up until, looks like, around 1970 or so. And the red line that's there is the growth rate, the percentage growth of the population every year. And something dramatic happened in around 1900. Population started skyrocketing globally. So you could imagine being someone who was looking at numbers back in the 70s, back in the 60s, looking at this, panicking. Because if you continue this curve, 3 billion, right, you just grow. I mean, what's going to happen in 40 years from the end of that diagram is how many, is it going to be 30 billion people? 50 billion people? Like, how many people are going to be on the earth? And that was a genuine concern. Now, the rest of the data, what does the rest of our table look like? So we're currently here. We're a little bit, well, actually got to aim a little better than that. We're currently there. And so we have all this data in red already. We have all this. We have this growth rate information, our rate of change, or our derivative of the population, in a sense. You can think of it that way. We have that data, and it supports the idea that our population is not going to do this exponential, explosion that people were worried about. It has inflected. It's reached an inflection point, and the growth will slow. And the debate, at least a reasonable part of the debate, is about whether or not the population is going to do this and maybe have a linear increase, if it's going to flatten out because we're reaching a true carrying capacity that we can't support anymore, or even if it will decline a little bit. Right? And how can it have a linear increase if there's a carrying capacity? The answer there would be there isn't a strict carrying capacity. The carrying capacity of the Earth is a function of how we live on Earth. So how much do we consume in terms of resources? How effective are we at leveraging technology to make better use of the resources that we have? And those are the types of considerations that would allow a population curve to not look like the population curve of bacteria in a petri dish or bunnies on an island. And the questions that are necessary to answer about the future of humanity aren't necessarily questions that can be answered with math, but math and mathematical tools are definitely part of the equation. Definitely part of definitely part of what's used. What we'll do in the next video is we'll talk about how to solve these types of differential equations, and then later on, the last thing we'll do in the course is we will go back to building mathematical models, posing those mathematical models in terms of differential equations, and then finding their solutions.